Hello students. At present, we all are crossing through a very tough time. The whole world is facing a challenge, that is COVID-19. And the only method or the only way to get rid of this challenge is to stay home. We are in a stage of lockdown for nearly 1.5 months. So naturally, we are detached from our regular classroom. This is a try to bring you back in the teaching and learning process. Today, in this video, I will discuss about the wave nature of light, which is an important topic of wave optics under the syllabus of ISC physics. According to wave theory of light, a source of light sends out disturbance in all directions. In a homogeneous medium, the disturbance reaches all those particles of the medium in phase which are located at the same distance from the source of light, and hence at any instant all such particles must be vibrating in phase with each other. Students, first of all, we have to learn what is wavefront. Wavefront is the locus of all such particles of the medium which are at any instant are vibrating in the same phase is called the wavefront. Depending upon the shape of the source of light, wavefront can be of following types. Number 1, spherical wavefront, number 2, cylindrical wavefront, and number 3, plane wavefront. First one, spherical wavefront. A spherical wavefront is produced by a point source of light. It is so because of the fact that the locus of all such points which are equidistant from the point source is a sphere. Students, you can see from the figure. Next is cylindrical wavefront. When the source of light is linear in shape, such as a slit, the cylindrical wavefront is produced. This is because all the points equidistant from a linear source lie on the surface of a cylinder. The third one is plane wavefront. A small part of a spherical or cylindrical wavefront due to a distant source will appear plane, and hence it is called a plane wavefront. Here we will discuss about a theory which is based on geometrical construction used to determine the position of a wavefront at a later time from its given position at any instant. This theory is known as Huygens principle. This principle gives a method to know as to how light spreads out in the medium. The principle is based on the given assumptions. Let me explain in a little detail. Consider a point source of light. Let AB be a section of primary spherical wavefront at any time t. In order to find the new position of wavefront at time t plus delta t, consider a number of points A, B, C, D, E on the primary wavefront. These points act as the source of secondary wavelets. In time delta t, light travels a distance c delta t. Taking points A, B, C, D, E as the centers, draw circles each of radius c delta t. These circles are called secondary wavelets originating from points on primary wavefront. Further, draw the envelope of the secondary wavelets. Parts A', B' and A''B' of the envelope are termed as forward secondary wavefront and backward secondary wavefront respectively. Then, as discussed here, A', B', the forward secondary wavefront, is the new position of the wavefront at time t plus delta t. The same procedure is adopted for finding the new position of a cylindrical or a plane wavefront. Students, you know that light has two specific properties of reflection and refraction, and we will prove those laws on the basis of wave nature of light. Here, according to this figure, we will prove the laws of reflection. Students, you follow the figure. Let XY be a reflecting surface and PA be a plane wavefront just incident on the surface. The normals LA and MP to the wavefront represent incident rays. If AN is normal to the reflecting surface at A, then angle NAL equal to angle of incidence. The wavefront reaches point A on the reflecting surface first. The wavefront will reach points between A and P' later in time, but in this order, so that it will reach point P' in the last. When disturbance from point P has reached point P' on the surface, the secondary wavelet from point A on the reflecting surface will grow into a sphere of radius AA', such that AA' is equal to PP'. To find the reflected wavefront with point A as center, draw a sphere of radius AA' is equal to PP'. From point P', draw P'A' tangent plane to the sphere. Then P'A' represents reflected wavefront and normals A'L' and P'M' to the reflected wavefront. P'A' represent reflected rays. Draw P'N' normal to reflecting surface at point P'. Then M'P'N' is equal to angle of reflection. To prove laws of reflection, consider any point Q on the incident wavefront. Suppose that when disturbance from point P on the incident wavefront reaches point P', the disturbance from point Q reaches Q' via point K on the surface. Since P'A' represents the reflected wavefront, the time taken by light to travel from any point on incident wavefront to the corresponding point on the reflected wavefront should always be same. If c is velocity of light, then time taken by light to go from Q to Q' is given by the first expression of time. Now, in right-angled triangle AQK, angle A is equal to angle of incidence, so QK is equal to AK sin I. Again, in right-angled triangle KQ', angle P' is equal to angle of reflection. Therefore, KQ' is equal to KP' sin I. Putting these values of QK and KQ' in the first expression of time, we get the second expression of time. Now, Kp' is equal to Ap' minus Ak. So we get the third expression of time. Lastly, we get the last expression of time, as you can see on the screen. For rays from different points on incident wavefront, the values of Ak are different. The rays from different points on incident wavefront will take same time to reach corresponding points on the reflected wavefront. If t given by the above expression of time is independent of ak, it will happen so if sin I is equal to sin r. So we can say I is equal to r. Thus, angle of incidence is equal to angle of reflection. Further, as the incident wavefront, the reflecting surface and the reflected wavefront are all perpendicular to the plane of the slide. Therefore, the incident ray, the normal and the reflected ray, which are respectively perpendicular to AP, XY and A'B' all lie in the same plane. This is the second law of reflection. Now, we will prove the laws of refraction on the basis of wave theory. As you can see in the figure, consider a plane wavefront AB incident on a surface XY separating medium 1 and 2, where 1 is air and 2 is the denser medium, at angle of incidence I as shown in the figure. Let the velocity of light in medium 1 be c1 and in medium 2 be c2. Obviously c2 is less than c1 as medium 2 is a denser and medium 1 is rarer. When the ray LA reaches A, secondary wavelets start from A which travel into the medium 2. Let t be the time taken by the ray PP' to reach the surface at P'. Then PP' is equal to C1t. During this time, the secondary wavelet from A travel a distance C2t in the second medium. Now draw an arc of a circle with center at A and radius C2t. Draw a tangent P'A' from P' to this arc. This represents the reflected wavefront. Consider a ray QKQ'. Now time taken by light to travel from Q to Q' is given by the first expression of time. Gradually, you will get the second expression as QK is equal to AK sin I and KQ' is equal to KP' sin R. Now KP' is equal to AP' minus AK, so you can get the third expression of time. Lastly, you can get the expression of time as you can see on the screen. The rays from different points on the incident wavefront will take the same time to reach the corresponding points on the refracted wavefront. It is possible only if t is independent of ak. Thus, we can give sin I by C1 minus sin R by C2 is equal to 0, as you can see on the screen. So from here we can say sin I by sin R is equal to C1 by C2 equal to mu2 1. Mu2 1 is called the refractive index of the second medium with respect to the first medium. This is nothing but Snell's law. Children, you can see that the incident wavefront, the refracted wavefront and the normal all are lying on the same plane. So here is the second law of refraction. Here is a worksheet based on today's discussion. So students, we have come to the end of today's topic and hope you have got a brief idea about what we have discussed today.